Okay, so this lecture is lecture 8. We're going to start looking at Markov chain Monte Carlo. So that's this lecture here. And what I want to do first, I guess, is say, obviously Markov chain Monte Carlo relies a lot on Markov chains. So I'm going to give you a quick overview of Markov chain Monte Carlo and remind you of some things that you need to know about Markov chains. So I think you should have come across many of these ideas before, but they're not too hard in any case. And we have some background readings here on Markov chains if you want more background on Markov chains. And so this lecture will kind of give you a high level reminder or indication of what you need to know about Markov chains. So before we get to that kind of review about Markov chains, let's just talk about, what's the motivation for doing Markov chain Monte Carlo. So we've already come across several problems where even maximum likelihood estimation is not analytically doable. So for example, in the empirical Bayes normal means problem, you had to use a numerical optimizer to find the maximum likelihood estimates for even a pretty simple version of that problem. And in mixture models, we've seen, we looked at using the EM algorithm for finding maximum likelihood estimates. So in neither case is it possible to find analytic estimates for the maximum likelihood estimators. So you can imagine that doing a Bayesian analysis of these models is also not analytically tractable. So far in our Bayesian analyses, we've focused on cases, simple conjugate computations where the Bayesian calculations can be done analytically. And so I'm just going to... so yes, we're going to... There are many problems where you can't do analytic Bayesian computations, and Markov chain Monte Carlo is going to allow us to do Bayesian computations in things like mixture models. So not just point estimates, which is what a maximum likelihood estimation would give you, but also give you some kind of posterior distribution on the parameters of the model, and so give you some idea of uncertainty, say, in those point estimates. Should say as well, like getting confidence intervals, classical confidence intervals, for example, for the parameters of a mixture model is also not straightforward. So a Bayesian inference there can help assess uncertainty in the parameter estimates. Okay, so that's why we might want to use MCMC. So what's the key idea behind MCMC? So the basic idea, and if some of these terms don't sound familiar, we're about to review them, so don't worry too much. But the basic idea is that we want to sample from some target distribution. It's usually called the target distribution that's hard to sample from. So for example, maybe we want to sample from the posterior distribution of the parameters of a mixture model, where it's not simple conjugate computation. Maybe it's not obvious why we want to sample from it. Maybe I should say that if you can sample from a distribution, you can compute almost anything you want for it. For example, the mean's very easy, of course, based on a sample of a distribution. You can also get variances, you can get probability, you can compute the probability that things lie in particular intervals. So the idea is that if we can sample from that posterior distribution, then we can summarize things like the posterior mean, posterior variance, get intervals from that sample. So, but the problem is it's also not easy to sample from those posterior distributions, just like it wasn't hard to just like it's hard to do the analytic calculations. So the idea is to indirectly sample by using a Markov chain, specifically create a Markov chain whose stationary distribution is the target distribution that we want to sample from. So loosely speaking, we're going to rely on theory that says that Markov chains, if you run them for long enough, they converge to their stationary distribution. That is, after a large number of iterations, we look at the Markov chain, it will be a sample from its stationary distribution. And since we've set it up as a stationary distribution to have the target we're interested in, it's also a sample from our target distribution. and it should be, you know, I should kind of mention, you know, there are regularity conditions for the Markov chain to converge to its stationary distribution, but actually in practice, the problem isn't usually satisfying those regularity conditions. It's usually in practice that we can, the difficulty of knowing whether we've run it for long enough. So let's just hold that thought until later when we start applying it in practice. You'll see we won't be worrying too much about satisfying regularity conditions, but we will be worrying more about whether we've run the Markov chain for long enough. Okay, so that's the key idea. Maybe there are some, you know, things you obviously need to know about Markov chains or be reminded about Markov chains. So here are the key ideas in this Markov review, and I'll spend the rest of this kind of video reviewing these ideas in the Markov chain review. Okay, so sorry, getting ahead of myself. Maybe I'll close off some of these ideas. So these are the key ideas, I guess. You need to know what the Markov property is. I'm going to just mention a very brief great thing about time homogeneous Markov chains. You need to know what a stationary distribution is, and you need to know that Markov chains under certain regularity conditions converge to a stationary distribution. You need to know what that means as well. Okay, so if you know all that already, you can stop watching now. But quickly, so what's the Markov property? Well, a series of random variables, sorry, I said to follow the Markov property, if the conditional distribution of the t+1th random variable given the first t random variables is equal to its conditional distribution given only the tth one. So in other words, in order to generate the t+1th random variable, it doesn't matter how you got there. All that matters is where you are at time t. So think about a Markov chain as moving around a state space. Each time it moves somewhere new, or possibly stays where it is. So that's sometimes called a transition. And the idea is that what the Markov property says is that the probability of transitioning to any given state depends on its history only through where we are right now, only through xt. So it's usually easiest to think about Markov chains as living in a discrete space, what we call finite state Markov chains. And most of the ideas then generalize naturally to situations where X lives in a continuous space. So I'll spend a lot of time talking about the theory or the basic concepts, assuming we're living in a discrete space. But in fact, when we come to apply these methods, we'll often want to have continuous space Markov chains, and I'll mention those occasionally briefly. But basically, the same ideas apply whether X is a continuous random variable or whether it's a discrete random variable. Same basic idea. So we'll be focusing on what's called time homogeneous Markov chains, which means that this transition probability, this probability that the next state xt+1 is j, given that the current state xt is I, doesn't depend on t. It's always the same, and so we can just call that Pij, and the matrix P, if X is discrete, then P is a matrix, and it's called the transition matrix. In a continuous space, you have the same idea. xt+1 will be a continuous random variable, so you need a density instead of a probability distribution, and we call the transition probabilities or the transition densities the density of y, or the density of xt+1 given that xt was X is called the transition kernel. Okay, so that's what a Markov chain is. So what's the great thing about Markov chains? There are lots of great things about Markov chains, but let me just highlight one particular great thing, which is they're super easy to simulate. Okay, so why are they so easy to simulate? Basically, because of this Markov property and the time homogeneous assumption, we just have to code up a method, a function, let's say, to create xt+1 given the current value xt, In other words, we just have to code up the transition kernel or the transition matrix, and then you generate a Markov chain by repeating that process. So you start somewhere, have to have somewhere to start, call it x1, and then you apply the transition kernel to generate x2 given x1, and then you apply the transition kernel to generate x3 given x2, and you apply the transition kernel to get x4 given x3, and you just keep applying the same transition kernel. So it's one function, as long as basically you have to write a function that takes as its parameter where you are now, and it gives you a random draw from where you go next. Let's think of it like that. So if you're not used to thinking about it in continuous space and you're finding that step going from a discrete to a continuous space a little difficult, just think about this as an example. This here, the xt plus 1 given xt is normal with mean xt and some variance sigma squared. Think of that as a way of getting around a space, a transition kernel. So wherever you are now, just to add a random normal 0 sigma squared to it, and that's where you go next. So that would be a transition kernel. That would be a simple to code transition kernel, and you could create a Markov chain by just repeatedly applying that to generate x2, x3 from x2, x4 from x3, etc. And in fact, this would be simulating Brownian motion, in fact. Okay, so that's, I guess I also want to say that when you come across new ideas or ideas you're less familiar with, in terms of distributions or stochastic processes, it's really helpful to think about how to simulate them, I think, in order to get your head around what they look like. So you know, this is another way of thinking about Markov chains. It's how do I simulate from a Markov chain? And the answer is you just repeatedly simulate a new value xt plus 1 given a current value xt using some rule, some random rule, such as this, a transition kernel, or if it's a discrete state, say using the transition matrix. Okay, so it's just kind of trying to solidify the idea of a Markov chain and the Markov property and how simple they are. So what's the stationary distribution? So this is a little more technical, so let's just remind ourselves what the definition of the stationary distribution is. And I'm going to do it in the discrete case, a Markov chain with a transition matrix P is said to have stationary distribution pi, where pi is a vector of length, a probability vector here, because it's a distribution and it sums to 1. And pi p equals pi. So pi is a vector, p is a matrix. So pi p is a vector matrix product. And so pi, you could say pi is a eigenvector of p with eigenvalue 1. That's another way of thinking about this. Okay, so what does that really mean though? Why is it called a stationary distribution if it satisfies that? Well, the basic idea is that if you start the Markov chain by sampling from pi, so pi is a probability vector, non-negative elements sum to 1. If we sample our element from the state space according to pi, according to that probability vector, and then run the Markov chain starting from that random starting point that we've just chosen, then every state in every random variable in that Markov chain will also be marginally sampled from pi. So that's the intuition, is that it's called the stationary distribution because if you start the Markov chain in that distribution, it stays there. It stays in that distribution. So if x1 has distribution pi, then xt will have distribution pi for all t, and that's this here. And the argument is not very complicated, and essentially you can go through this on your own time, but if x1 is simulated according to a distribution q, then x2 comes from qp by the law of total probability, essentially. So if applying that to q equals pi, if x1 is coming from pi, then x2 is coming from pi p. And since pi p equals pi by definition of pi, that means x2 is coming from pi. And then by induction, xt is coming from pi for all t. Okay, so it's the idea of a stationary distribution. Again, if you start the Markov chain, if it samples from a stationary distribution, the first state, then all subsequent states will also be sampled from that same distribution marginally. Okay. So that's what a stationary distribution is. And the last thing you need to know is about convergence to a stationary distribution. So, and you don't really need to know the careful technical conditions under which this occurs, but there are some regularity conditions you need. But under those regularity conditions, the distribution, I've used n here, maybe I should use t. The distribution of state t will converge to pi, whatever the starting state. So let's replace this with t here, because I'll go back and do that after I finish this video. So what that's saying is that essentially, if we run the Markov chain long enough, that is, if n is big enough here, then the probability that xn is equal to j will be very close, or will approach in the limit pi j. Okay, whatever we start. So although I motivated the stationary distribution in terms of if you start there, you stay there, that's true. Under additional conditions, wherever you start, you'll eventually start sampling from the stationary distribution. That's kind of intuitive, is that if you do it for long enough, it gets close to the stationary distribution. Once it gets close to the stationary distribution, it stays close to the stationary distribution, actually gets closer to the stationary distribution, because the stationary distribution is the kind of fixed point. Once you get there, you stay there. And so this is kind of the intuition behind why you might expect that to happen. So that means that you can approximate expectations under pi by essentially by averaging across a long realization of a Markov chain. So that's what this is about, right? The average of f along the trajectory of the Markov chain. So xi here is the different states in the Markov chain, or the realized states in the Markov chain, x1, x2, x3, etc. So if we just compute f for each state we see and average it, because in the long run x will come from pi, in the long run this will converge to the expectation of f under pi. Essentially says you can kind of treat the realization of a Markov chain as a sample from pi. This, if the x's were independently sampled from pi, this would clearly be true by the law of large numbers, right? And so these are not independent samples from pi, but it's still true under regularity conditions. So the way you can think about that is, although the x's are not independent, they're forming a Markov chain. If you run them long enough, they kind of behave a bit like the independent ones in the long run for independent samples from pi, in the sense that they, their average behavior is the same. Okay, so what can go wrong? Let me just briefly say why might a Markov chain not converge to its stationary distribution? Well, one reason it might not converge is that if it's reducible means it can't get from everywhere to everywhere else. So we'll see an example of that in a minute. And another reason it might not converge is if it's periodic. So let me just give you examples of those. In practice, these don't come up very much in Markov chain Monte Carlo, but it's just good, it can come up, and it's good to know what these mean. So we can just have a Markov chain on 0 and 1. These are the two states. So we need a transition. So let's imagine one where if it starts in 0, it stays in 0, and if it starts in 1, it stays in 1, and it never jumps between them, right? So P here, the chances of going from 0 to 0 is 1, and the chances of it going from 1 to 1 is 1, and it doesn't transition, okay? So actually any pi will satisfy pi p equals pi here. So it has, the stationary distribution is not uniquely defined. And because the chain can't move between 0 and 1, it doesn't converge in general to the, well, it stays where it started. So, so here, this is what's called a reducible Markov chain, because you can't get from any state to any other state. So you don't have to be able to get, in order for it to be irreducible, you don't need to be able to get from every state to every other state in one jump, but you have to be able to get there eventually. So let's give an example of one. So if 1 either stays where it is or goes to 2, and 2 either stays where it is or goes back to 1, and then 1 either stays where it is, we'll change it so it goes to 0, and 0 either stays where it is or goes back to 1, then there's no direct link from 0 to 2. You can't jump directly from 0 to 2. But you can get from 2 via 1, so that's fine. That's not irreducible. So that's not reducible. Okay, so this would be fine. This would you can get from every state to every other state eventually, and that's what you need. Periodic Markov chain. So here's, what if every step you change? So you just always jump. So this is periodic because if you start at 0, then it will return to 0 every 2 steps, and it will be at 1 every 2 steps as well. And so it never, because of that kind of periodicity where you're only ever in it every 2 steps or every k steps, let's say, that can all, that kind of behavior would also stop it converging to a stationary distribution. And in practice, I would say I've never come across a MCMC problem where this is anything to worry about. There are MCMC problems, some subtle ones where you have to worry about being able to get from every state to every other state, but usually even that's not hard to ensure. Okay. All right. So that's the end of that review, and the next thing we'll talk about is the Metropolis Hastings algorithm.